are almost there at the end. One more presentation, and it's going to be a little interactive, so we'll keep you awake. That's my goal. Like Andy said, I'm a geobiologist at the University of California at Davis, and I was lucky enough to marry someone finishing their PhD at UNM, and so I've spent the last year of my PhD out here finishing writing and working with the rover, the Curiosity rover, in Curtin Newsom's Operations Center here at UNM. So it's been really nice to come back and spend time here. And so one of my favorite things to talk about is water on Mars. And it's what everyone wants to know. Is there water? Was there water? Could there be life? Could humans live on Mars at some point in the future? And so I want to give you kind of a brief introduction to what we know about water on Mars and what we hope to learn using the Curiosity rover. So as I'm sure you've heard over the past few days, both Earth and Mars are rocky planets. They're about the same age. But as you can see, they have evolved very differently. And so what I want to talk about is how they've actually started the same way, become these two very different planets. And Mars provides a really interesting natural laboratory for us to understand what Earth would be like without that biosphere, without all of that water contributing to our ecology. And so I want to take a quick poll, and I'm pretty sure you guys have talked about this a lot this week, but can I see a show of hands for how many people believe that there was water on Mars in the past? All right, getting something out of this presentation. Excellent. Now here's the tricky one. I want to see a show of hands for people who think that there is water on Mars today.
Are you qualifying that in any way?
Not qualifying in any way. Is there water on Mars today? Do you think there's liquid water on Mars today? We'll qualify it now. Yes, it's for liquid water on Mars.
Maybe.
Okay, so I'm seeing maybe a third of people with the iffy hand. All right, well good. Then we'll learn something today from this presentation. So this is a MOLA picture, or a picture that shows the altitude of the different landforms on Mars. And what you might notice here is that there's actually big basins, which are these blue areas, both in the northern hemisphere and this big basin in the southern hemisphere called the Hellas Basin. They actually be really great places if you want to have lakes or seas. And there are some people within the community who think that at one point in Mars' early history, you may have had a large northern ocean in those northern lowlands, possibly even a large sea in the southern hemisphere. There are some people, like I said, in the community who think that, some who say, there's not really great evidence for that. But that's where the science comes in. Let's look for the evidence of features like a large ocean or a large sea. Let's look for evidence of water on Mars. And so I'd like you to do a quick 1 minute think, pair, share. Turn to your neighbor or in groups of 3. I want you to brainstorm 1 or 2 types of geologic evidence. What would you look for if you wanted to show, to prove there was water on Mars? So let's take 1 minute to do that. We'll take 1 minute to share.
Wait till I break things down.
Ready, set, go.
Sorry. Oh. No, I'm glad. Layering.
30 more seconds.
What about those irons and spherules? But they were saying that would be through water. And you talk about leaching of minerals. Blueberries? What about raspberries?
Okay, time. So can I have some volunteers? Would you mind sharing with me what lines of evidence you've come up with? Do I have to
I'll
assign
do
a
it.
speaker? Okay, sure.
We said a bunch of things. You just want one of ours?
Give me a couple, sure.
Rounded rocks, and then hydrated minerals, layering and sedimentation.
Okay.
We'll let the other groups finish.
All right. Other options?
We said
deltas and channels, okay. Anything else? All right.
Sedimentary rock.
Sedimentary rock, right? Layering of the rock or sed rocks, that's absolutely right.
Leaching.
Leaching? All right, this is a pretty good list. So I would agree with you. These are great lines of evidence. And I'm going to go into a little more detail on some of these. I'm going to expand on some that you haven't listed here. And my goal with this is hoping that you'll have a few lines of evidence in hand that you can take back to your classrooms and say, this is evidence for water on Mars. Here's how we know. Here's how we move forward and move for water on Mars in the present. All right. So let's step through a couple of lines of evidence for water on Mars. There are two broad umbrellas of evidence that I'm going to talk about today. Those that are detected through satellite observations, things like the high-rise camera, the very high-resolution camera on board the Mars Reconnaissance Orbiter, and then ground-level observations, things that are detected by the Mars Exploration Rovers and the Curiosity rover. So I'm going to start with satellite-level observations. Now, what most of this is based on is geomorphology, which is the study of landforms and the processes that make those landforms. And so the three lines of evidence I'm going to talk to you about today are inverted paleochannels, alluvial fans, and deltas. I'm curious, has anyone heard about inverted paleochannels yet? All right, great. So the first line of evidence, like I said, are inverted paleochannels. Now these form from erosion, specific erosion around a feature. And so I'm going to draw a quick diagram to show you how a structure like this might form. So if you originally have a river channel, say we have, this is the ground surface, here's some trees, we're clearly not on Mars now, and say this is a water level. Over time, you can imagine pebbles and rocks moving through that channel and depositing. Over a greater amount of time, the rocks may fill up the channel, maybe as water starts to dry up and there's less water available, and smaller minerals will cement those rocks together so they're a big, solid mass. So you eventually have this being pretty solid. Now what happens over time is differential erosion will remove either the material that surrounds that river channel or the river channel itself. Now which one's going to be more resistant, the cemented material or the loose material? So the loose material, these layers, are actually going to erode away. And so what you end up getting over time is a preserved feature that starts to stick up above the landscape. And so you eventually have an inverted, meaning the topography is inverted instead of the river being in the ground, it's above ground, an inverted paleochannel. It's an ancient channel. And so I've got two examples here, one from Gale Crater, which is where the Curiosity rover is now, and actually one out in Utah. You can see where the river channel once was. Part of the indicators that that was a river channel in both of those instances are the presence of meanders, or the way that the paleochannel kind of bends and curves. And so that preserved feature, those meanders are being preserved above ground. That's a great indication that there were rivers flowing on Mars in its past. So the second line of evidence that I want to talk to you about are alluvial fans. And I think some people brought up deltas, and alluvial fans form in a very similar way. And so here are two great examples, one from Holden Crater and one in China. And so what you can picture is water flowing in the channel right here, and pouring out into this flat area. You see the same thing, there's a small channel here, and the water would pour out and deposit rocks that it's carrying. And so if you think about, if you are flying overhead like in these images, you picture a mountainous area. Channels are pretty deep and pretty narrow, right? So they have a lot of energy and they can carry very large rocks. And when you hit a flat area, say you're at the edge of a mountain, and then this is a valley, the water is going to spread out, and that energy is going to disperse, and those rocks are going to fall out of the water column. So even though you're flowing really, really fast here, you disperse your water out this way. And you form these distinct low structures. So alluvial fans are just water-carrying rocks that dump out onto a plain somewhere. And I have a video, actually, that decides to work. Here we go. That same thing. The water is pouring out of this little pipe right here, and you can picture that being the edge of the channel on the edge of a mountain. And it pours out into the flat area and distributes itself as a lobe of sediment. It's a very distinct indicator that water was present in an area. So the third line of satellite evidence are deltas. And deltas, like I said, form very similarly to alluvial fans. But in this case, instead of dumping out from a channel, a narrow, deep channel onto a plain, they're dumping out into a body of water. You get this more distinct multi-lobate structure. This is an example of the Eberswalde Delta, an Eberswalde crater. And this is an example of the Birdfoot Delta. I think this is actually the Atchafalaya in Louisiana, but the Mississippi River Delta forms in a very similar way. And so you can see that distinct structure where there are these kind of streamers that move out into the water body, and you have sediment depositing there. So what was really unique when we found this type of structure in Eberswalde is that this indicated that a river, first off, carrying water and sediment, was pouring into a larger body of water in Eberswalde. So we have now two lines of evidence in one given area for water on Mars, specifically at Eberswalde. There are other deltas that have been identified as well, and this is one of the best preserved ones. So, I'd like to take 90 seconds and have a group discussion at each of your tables. I want you to discuss and decide if any of these lines of evidence is most convincing to you personally as evidence for water on Mars, and give a reason why. So we're going to discuss for 90 seconds and then we'll share for 90 seconds. So discuss with your group which of these lines of evidence do you find to be the most compelling. Okay, time. So have we reached consensus at our table? Still a lot of discussion. Still some discussion? All right. Can I see a show of hands then? How many people think inverted paleo channels are the most compelling line of evidence? No one. Wow. All right, I'll take two. Alluvial fans? I've got 2, 3, 4 for alluvial fans, and deltas. Everyone else. Most. Excellent. And so would someone be willing to share why they found, whichever of these they found most compelling? Why is it so compelling to you that you're willing to say deltas, absolutely, or inverted paleo channels, definitely? Will anyone share?
Well, we decided that for deltas, you have to have two sources of water. You have to have the water flowing and the water that's flowing into,
Yeah. So you think two separate lines of evidence in one area makes it the most compelling. That's very reasonable, absolutely. Anyone else want to share?
We just don't know if there's anything that could, like, I don't know if lava flows could mimic alluvial alluvial fan for the delta, but we couldn't come up with anything that would mimic the paleochannel. But could be just our lack of knowledge too.
I think that that's very reasonable. It's great to look at the other options and be able to rule those out, and that is a very important line of evidence in working with argumentation to say definitely this is the only way something could form. So I agree with you. I think paleochannels are also a really great option. Yes.
Within alluvial fans, do you see grading? Do you see the larger at the beginning and then finding outward?
You can, yeah. And so the trouble, pardon?
That would help.
That would convince you more. That's absolutely right. If it's made of sediments instead of made of pure basalt, absolutely. And from orbit, as you can tell, it'd be very difficult to tell that. And that's where we come up. That's actually a great segue to looking at things from the ground level and why it's so valuable to send rovers that can look at the ground level structures. Did I have one more comment?
Well, yeah, just a question about the numbers of these things. Do you notice more on the surface of Mars, more of the deltaic features, the alluvial fan features, or the alluvial channels? Is there like a number that you have?
You know, I have no number. I can tell you
One more common than the other?
I've seen a lot of alluvial fans in Google Mars. It's very easy to pick those out. Like I said, there are a handful of deltas that have been identified as well.
Are they in the blue area? You know, the lower level area? Backing up
Eberswalde is not, and I can't think of the location of the other deltas right now, but that's kind of on the border with the northern lowlands, but it's not in them. It's not in them, yeah.
It just seems that the channels would be like really specific set of conditions within the form.
How do you mean?
I don't know, it just seems like everything would have to be exactly right. They'd have to have the right amount of, the right types of sediment inside the channels.
Oh, the inverted paleo channels?
Yeah. To solidify.
Yeah, there can be differential preservation. You're absolutely right. Yeah. So maybe more formed, but they existed, but they weren't preserved. And preservation potential is a huge issue in interpreting the ancient environment on Mars. You're absolutely right. So this is the part that's near and dear to my heart, looking at the surface of Mars on the ground level and using NASA's rovers to do that. And I'm sure you've seen this image in the past couple of days. These are the 3 rovers that we have sent to Mars. The first was Sojourner in 1996, and she was part of the Pathfinder mission. And that goal was just to prove that you can land a rover on Mars and it can rove and you can make it work. And so once we ground truthed that, we were able to send the Mars exploration rovers, Spirit and Opportunity, and I'll go into a bit more detail on them, but they really took us light years ahead of where we were in our understanding of Mars. And because of the work that they did, we were able to build and send out the Curiosity rover. And of course, that's the mission that I'm working on, and we've been able to determine quite a lot about the ancient water on Mars, in fact, water on Mars today, and what it would take for life to want to live in certain environments on Mars. Now I'm going to step through, again, 3 lines of evidence for ground level observations of water on Mars. And these are based, instead of being on geomorphology and landforms, instead on sedimentology, which is the study of sediments and the processes that control their deposition. And the 3 lines of evidence I'm going to share with you today are hematite concretions, or blueberries as they've been called on Mars, gypsum veins, and rocks called conglomerates. And so let's start with the first line of evidence. This is an image of the hematite blueberries, or concretions, both on Mars on the left at Meridiani Planum, and then in Utah actually on the right. Now these concretions form only by interacting with water. And so what happens is you have a porous sedimentary rock like a sandstone. If you picture a sandstone, it's made up of sand-sized grains, and there's actually pores between each of those grains, enough space for water to just move through. And so what the groundwater does when it moves through that sandstone is kind of pick up iron and then deposit it in select areas, and that's normally because there's some kind of nucleation site. There's one spot, maybe a little piece of iron hasn't been mobilized, and the rest of the iron is going to stick to it. And so you get these spheres that grow that look like this. And there's actually a really great image from Meridiani that shows the spheres. It's in the sandstone. You can see there's a dot right there, a couple of dots down here, but you can see how they erode out and they collect in the low points on Mars. And we see the exact same thing where those blueberries are found in Utah. So they're definitely features that form by the mobilization of water. The second line of evidence I wanted to share with you is the presence of gypsum. Gypsum forms from flowing water, sometimes at a bit higher temperatures, sometimes like in the sense of like a hydrothermal system. And I had this really great quote from Steve Squires, who's the principal investigator of the Mars exploration rovers. He said, "There's a fracture in a rock, water flowed through it, gypsum was precipitated from the water." End of story. You really aren't going to get a vein, which is what we call one of these kind of long structures in the ground mass here. You're not really going to get a vein like that in any other way. It's incredibly indicative of the presence of water. And gypsum really forms from water in multiple environments on Earth. And so the third line of evidence are the presence of river conglomerates. Has anyone seen this image before? This is actually a really characteristic, really great image. I see some head nodding. You've seen a lot of red rocks? Would you believe me if I said this is actually from Earth? Yes? I'd be pulling your leg. This is actually an image from Mars. This is one of the most distinct examples of conglomerates that we found when we first landed with the Curiosity rover. And I'm going to zoom in on this area right here. This is an image of a conglomerate on Mars and an image at the same resolution from Earth. And we know that water formed these rocks because you see these big grains in the rock and big grains that have fallen out of it and are covering the ground here. The only way to move grains of that size is with water. They're far too big for wind to push them. And so we know that enough water flowed to move grains of that size, and then they were cemented in place. That's what the kind of this white material around it is. And that's really incredible evidence for water on Mars. We can actually figure out based on the diameter of these grains and how rounded they are that the water that deposited these rocks was about ankle to hip deep. That's a decent amount of water on Mars. And we know it wasn't one pulse and that's it, no more water. This was something, it was episodic, but it happened again and again. So conglomerate rocks are really fantastic evidence for water on Mars. And so I want to take 90 more seconds, talk again about which of these three lines of evidence your table or you personally find the most compelling, and we'll do another poll real quick. So let's go ahead and start.
Just curious as to, is the only way that those conglomerates form underwater? Is that the only
Like through water flowing?
Is that the only possible?
Water forms the conglomerate. Liquid water is your preferred method of moving something. You get a different type of deposit from, say, a glacier picking up rocks and depositing it somewhere. That's going to look very different from what we've seen, what we're calling conglomerates in that area of Gale Crater.
So yes, that's the only way it's going to form like that.
Exactly like that. We're pretty convinced it's a river, a fluvial system, a river system.
In the store.
All right, so we've gone way over. Can I get a quick poll from folks? do folks find blueberries to be the most compelling line of evidence? Anyone? Okay. Gypsum veins. Not even poured gypsum. All right. Are we all voting for conglomerates then?
Really, all of the above.
Yeah, absolutely.
Yeah, true.
It is, and that's why you've seen these lines of evidence. We want you to think about, if you were the student and you saw these three, which one would convince you the most? Which one would you really latch on to? And which would be the easiest to get someone started thinking, well, this was deposited by water. What about blueberries? What about gypsum veins? And so I agree the conglomerate is very, very telling. We're very lucky to have found it so early in the Curiosity mission. Yes?
Question with blueberries, is the sandstone submerged in the water for that to form? Or is it just water flowing over the surface?
It's subterranean, and it's groundwater that's just slowly moving through the pores.
So it's under the earth.
Yep, it's under the earth.
Not like a manganese nodule that's just sitting in open water.
Right, yeah, and there's a bit of a difference between how manganese nodules can form, and they can be similarly formed, but we haven't found any manganese nodules that we know of yet on Mars. That would be extremely exciting. Okay, so what I want to share with you now is a quick discussion on where did the water go. So some of it is frozen, but it can thaw. I see a picture down here where you guys have already looked at this one image. This is a picture of solid ground ice that the Phoenix lander dug out of the ground at one of the poles. The average temperature on Mars is about negative 65 degrees Fahrenheit. At the poles in winter, it gets down to negative 200 Fahrenheit. But given all those temperatures, the Curiosity rover has actually seen temperatures just above freezing in Gale Crater. And that's about at the Martian mid-latitudes. That's in the middle of the summer. But you can get above freezing. And in fact, the Phoenix lander took pictures of these little drops that formed on one of its legs. This is liquid water that formed for a very short period of time. It condensed out. It formed on the legs. We got some pictures. We saw how some of these drops coalesced. And then it was gone. So you can have periods of time when the relative humidity is high enough, the temperature is high enough, you can have short-lived spurts of liquid water on Mars. There's actually an even better example of this. What we see in crater walls, so if you picture you're standing in a crater and looking up at the wall, which is what you're seeing here, you see that there are these dark lines that are coming down the edge of the crater wall. These only form in the spring and summer, and we see them using our high-resolution cameras on our orbiting satellites. And what we believe this is an ice layer below ground that is melting in the spring and summer and forming these little flows of water, and then they're gone. They're very ephemeral, but we see them, we take multiple images and see them moving down the crater wall, and then they're gone, only in the spring and summer. So again, another line of evidence, we believe that there is episodic liquid water on Mars today. So where has all the water gone? The problem is that Mars has a very thin atmosphere, especially relative to Earth. Mars once had a thicker atmosphere, and that's capable of retaining that water vapor, but it's been mostly blown away by solar winds and large impacts. And this is actually an image of Earth and how our atmosphere is protected by our magnetic field from solar winds. And because Mars no longer has really a magnetic field, it doesn't have that protection. There wasn't any way to really keep a thick atmosphere around. And the question that I'm always asked in outreach talks is, what about Martians? Could there have been life on Mars? Is there life on Mars? Could humans ever inhabit Mars? So on Earth, we know that where there's water, there's always life. Even at the bottom of the ocean, even in boiling hot springs, life, things like bacteria and archaea can live there. And so our first mission, landed mission to Mars, Viking, was a life detection mission. You can imagine we were pretty disappointed when we didn't immediately find life. So we stepped back and revamped our approach to exploring Mars. We sent the Pathfinder mission with the Sojourner rover to explore the area and then say we can also use a rover on Mars. We sent Phoenix to look for ground ice at the poles, and we found it. We sent MER in 2004 to follow the water. That was the goal of the Mars exploration rovers. And they found incredible evidence for water on Mars in its past. And so all of this behind us, we started thinking, well, what's the next step? What's the next thing that we can explore and find definitive evidence for on Mars? And so we built the Curiosity rover to search for a habitable environment on Mars, one in which life, like bacteria, would want to live or could have lived in the past. And so the three things that organisms like bacteria need on Earth to survive are water, a source of carbon, and a source of chemical energy. It could be light energy. A lot of the time we say because there might be issues with UV radiation, there might be issues living at the surface. Organisms also live below ground and can use chemical energy to survive. And so those are the three things that we wanted to identify to find a habitable environment on Mars with the Curiosity rover. And so what we did is landed in Gale Crater. We landed at this kind of dark spot right here at Bradbury Landing, and this is where the jets on our landing pack blew away the sediment around us. And if you look closely, you can see actually the rover tracks in the sand where we started heading toward an area we called Yellowknife Bay. Now we went over to Yellowknife Bay because we could tell that it was the lowest point in this area. And if you want to find where water was at its very last point, you want to go downhill. You want to look in the lowest point. So we went over to Yellowknife Bay to look for a habitable environment. This is an image of us entering Yellowknife Bay. And here's one of the rocks we found just outside of Yellowknife Bay. We call these the Shaler rocks, all of them together. They're very fine-grained, they're tilted, they actually show some cross-bedding. All of these are indicative of deposition by water in this environment. So great, you know, we found an area and geologically it looks like there was water here. That's what the rocks are telling us. We also found evidence, again, for veins that are very similar to gypsum. They're also made of calcium and sulfate. And we found them in the rocks at Yellowknife Bay. And here's a picture of the very similar veins that form on Earth. So again, more lines of evidence for water at Yellowknife Bay. And lastly, we found these features that we called spherules. They are different from the blueberries, but they are also these concretions that tell us that groundwater percolated through the pores in this rock, formed these structures. We have more and more evidence for water at Yellowknife Bay. And so to better understand whether this environment was habitable, we deployed our arm. So this is our arm sticking out, and we used our drill to drill actually the first drill holes on Mars at that point. We've drilled since then. This is really an incredible technological feat all of its own. We ingest the sediment that we pulled out of these drill holes, and here's a summary of what we found. We found that geology, those fine-grained rocks, all of this indicated that this was an ephemerally wet area, that it might have been actually a lake bed, and that it's definitely at the base of kind of a fluvial or river system. So we know there was water here. The minerals that we determined were present in that rock indicated that there was liquid water that wasn't very acidic, it wasn't too alkaline, and it wasn't really salty. So that's kind of a circumneutral water environment that life would probably like to live in. We also found all of the chemical ingredients necessary for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And we also found that the minerals present in that rock were of two oxidation states. There was actually oxidized sulfur and reduced sulfur. And if you want a chemical source of energy for microbial life, bacterial life, they can actually use those two oxidation states and get energy from it and survive. So at Yellowknife Bay, within our first 7 months of landing, we found the three things that life on Earth requires to survive: water, carbon, and a source of energy. Not to say that there's life there now, but that it was a habitable environment in the past. And so, just to give you an idea of how far we've come from there, that was within the first 7 months of us landing on Mars, and we are approaching our 2 years of being on Mars with Curiosity. We landed way up here, and we traversed over to Yellowknife Bay. And since then, we have come all the way down here, and actually just finished a campaign in an area we called the Kimberley about a month ago. This was another area with evidence for abundant water in the past. But that's not our final destination. We are actually heading toward Mount Sharp, which is in the middle of Gale Crater. It's a very cryptic mountain, and we're interested in what it can tell us about the ancient environment on Mars. So you can see where we landed, where we went to Yellowknife Bay. We just left the Kimberley here, and we're heading all the way down here to the base of Mount Sharp, and we're going to traverse up what we're calling the Grand Canyon here and explore the layers of rock that are preserved in Mount Sharp. And these are some of the things that we're interested in. There are all these different layers we've detected from orbit, including something that has a lot of hematite in it, a layer that has a lot of clay, and then a big layer that has a bunch of sulfate. So this is really interesting because we know clay is deposited by water, and we believe that sulfate indicates a drying environment. So what we may be seeing here, what we may have captured, is the transition from that young, early wet Mars to the dry, arid Mars that we know today. And so our goal is to traverse up the mountain and explore those units and determine what kind of habitable environments are preserved there. And so I know we're running a little quick. Yes, see, we have a few minutes. I wanted to take a minute and have you reflect on which of these lines of evidence, or multiple lines of evidence, you would be interested in incorporating into your classroom if you were to conduct an activity to teach your students about water on Mars. So just 3 minutes, a little reflection. Which of these lines of evidence would you be interested in? What would be your learning goal, your assessment, and your activity? And then we'll take a couple of questions. So take maybe 2 minutes and reflect on what you think would be the most compelling line of evidence to share with your students.